partial pressures. Dalton's law of partial pressures. Dalton's law of partial pressures. Suppose you take a mixture of two gases, say in a cylinder or in a vessel, there is a mixture of gases. Gas A and gas B. Two gases are kept in a vessel like this. And the gas will be exerting a pressure. The pressure due to this gas mixture is due to the pressure of the individual gases. The pressure due to each gas, individual gas, that is known as partial pressure. If we have a mixture of gases, a mixture of non-interacting gases, the pressure due to each gas is called the partial pressure. So partial pressure is equal to the pressure due to each gas, that is called the partial pressure. So gas A, it is exerting a pressure inside this volume, and it is called the partial pressure of A. We can say call it as PA, that is the partial pressure of A. Pressure exerted by B, you call it as partial pressure of B, PB. Now, you measure the total pressure of the gas mixture. The total pressure of the gas mixture, we can call it P total. Total pressure due to the gas mixture. It is equal to the sum of the partial pressures of the individual gases. And that is Dalton's law of partial pressures. In a gas mixture, each gas will be exerting a pressure. The pressure due to each gas, that is called the partial pressure of that gas. And according to Dalton's law of partial pressures, the total pressure exerted by a mixture of non-reacting gases is the sum of the partial pressures of individual gases. Suppose we have a mixture of A and B, two gases. The non-reacting gases A and B. Let the partial pressure due to A is equal to PA. Partial pressure due to B is equal to PB. Then the total pressure of the gas mixture PT is equal to PA plus PB, and that is the Dalton's law of partial pressures. So P total of a mixture of gases is equal to the sum of the partial pressures of the respective gases, the individual gases. So PT is equal to PA plus PB. If there are three gases, then PT is equal to PA plus PB plus PC, like that. The sum of the partial pressures is equal to the total pressure of the non-interacting gas mixture. Now we can apply this Dalton's law of partial pressures in the case of moist gases. Moist gas. You take a moist gas. And what is a moist gas? A moist gas is not dry gas, it contains moisture. A gas containing moisture. So moist gas is equal to dry gas. Dry gas plus moisture, water vapor or moisture. And that is a moist gas. So in the moist gas, the total pressure of the moist gas, that is PT, that is equal to the sum of the partial pressure of a dry gas P, and the partial pressure due to moisture. Partial pressure due to moisture, this is called, that is known as aqueous tension. That is called aqueous tension. Aqueous means water. Tension means pressure. So the pressure due to water vapor, pressure due to moisture, that's called aqueous tension. So if we apply Dalton's law of partial pressures, in the case of a moist gas, the total pressure of the moist gas PT is equal to the pressure due to the dry gas P plus pressure due to moisture, that is aqueous tension. So PT is equal to P plus aqueous tension, where PT is the total pressure of the moist gas. P is the partial pressure due to the dry gas. Or you can say it is the pressure due to dry gas. And aqueous tension, that is the pressure due to moisture or water vapor. So to get the pressure due to dry gas P, what you have to do? Say you have to subtract the aqueous tension from the pressure due to moist gas. From the pressure due to the moist gas PT, you have to subtract aqueous tension so that you will get the pressure due to dry gas. So we can apply Dalton's law of partial pressures in the case of moist gas. Okay, let us see the relation between partial pressure and mole fraction. The relation between partial pressure of a gas, partial pressure, and mole fraction of the gas, mole fraction. Do you remember what's meant by mole fraction? Mole fraction of a component X, XA, for example, XA, that is equal to number of moles of A divided by total number of moles, say Na plus Nb, if there are two gases. So XA, that is the mole fraction of A, that we have studied in the first chapter. In the first chapter we have studied, mole fraction is the ratio between the number of moles of the components and the total number of moles of all the components. The ratio of the number of moles of the components and total number of moles of all the components. Suppose we have two components A and B. Suppose we have two gases A and B. Then the mole fraction of A, XA, is equal to Na plus Nb. So Na, number of moles of A, and Nb, that is equal to number of moles of B. Similarly, the mole fraction of B, that is equal to number of moles of B, Nb, by total number of moles, Na plus Nb. So the ratio between the number of moles of each component and the total number of moles of all the components, that's called the mole fraction. If you have two components, if you have two gases, then the mole fraction of a gas A, XA, is equal to number of moles of A, Na, by total number of moles of A and B, Na plus Nb. Similarly, the mole fraction of the component B, gas B, is equal to XB, is equal to Nb, number of moles of B, divided by total number of moles of the two gases, Na plus Nb. Now, let us see the relation between partial pressure and mole fraction of a gas. The relation is this. Say, partial pressure of A is equal to mole fraction of A into P total. P total. Partial pressure of A is equal to mole fraction of A into total pressure P total. Similarly, partial pressure of B, PB is equal to mole fraction of B, XB into P total, PT. That is a partial pressure of the component B. So we can have a relation between the partial pressure of a component and the total pressure. Say partial pressure of a component is equal to the product between the mole fraction of that component and the total pressure. If XA is the mole fraction of the component A and XB is the mole fraction of the component B, and PA and PB are the respective partial pressures. Then PA, partial pressure of APA is equal to XA into PT, where XA is the mole fraction of A and PT is the total pressure. Similarly, partial pressure due to B, this PB, is equal to the mole fraction of B, XB, into total pressure, PT. That's the relation between the mole fraction and the partial pressure of the components. See, now let us see the case of real gases. Let us study the deviation of real gases. Deviation of real gases. Say a gas which obeys Boyle's law and Charles' law. That is an ideal gas. So an ideal gas always obeys. An ideal gas always obeys Boyle's law and Charles' law and all the other gas laws. And the gas equation also. PV is equal to nRT. PV is equal to nRT. An ideal gas obeys that equation also. PV is equal to nRT. If it is so, from Boyle's law, we have got a relation. At a constant temperature, PV is equal to constant. PV is equal to constant at a constant temperature. And this is from Boyle's law. This statement, this is the mathematical formulation of the Boyle's law. PV is equal to constant at a constant temperature. If it is so, if we plot PV against pressure or volume, what is the nature of the graph obtained? Do you remember? Anybody remembers the graph between
line parallel to
PV?
x-axis.
Punya, do you know the nature of the graph? That is from
Line
Boyle's
parallel
law.
to x-axis.
It is a straight line. PV is a constant. PV is a constant. So it should be a straight line parallel to the pressure axis. Or you can plot the volume also. Here you can plot the volume. So a graph of PV against P or PV against V, that is a constant, it's a straight line. It's a straight line. And this is from Boyle's law. This statement is from Boyle's law. Boyle's law. PV is constant from Boyle's law. So this is the nature of the graph obtained if the gas obeys Boyle's law or if the gas is an ideal gas. So the graph for an ideal gas is like this. Okay. So PV against P or PV against V. For example, you take a PV against P. That is a straight line parallel to the pressure axis because PV is a constant from Boyle's law and that is for an ideal gas. But for real gases, if we plot PV against P, it is not always a straight line. It is not always a straight line. See, in some cases, the PV against P, that graph is, say, the graph will be, say, this is for ideal gas. Okay. So for a real gases, if PV is plotted against P, in some cases, you can see a straight line, but it is going up. That means PV is greater than that expected for ideal gas. And this type of graph is obtained for, this type of graph is obtained for, say, gases like, say, hydrogen, helium, etc. Say, for example, hydrogen, the graph is like this. Okay. For some gases, the PV value first decreases. It reaches a minimum and then the value increases. This is seen in the case of carbon monoxide, then CH4, etc. CH4, we get the graph like this. So for real gases, a graph between PV and P is not always a straight line. Say the graph is found to be either a straight line, it is going up. That means PV is greater than that expected for an ideal gas. And this type of a deviation, that is called the positive deviation. This is called positive deviation. So the curve shows, the graph shows positive deviation. PV is always greater than that expected for ideal gas. For example, hydrogen or helium. Similarly, take methane CH4 or carbon monoxide. In these cases, first the gas shows, say, a depression, a lowering in the PV value, a lowering in the PV value, and it reaches a minimum and then increases. If there is a lowering in the PV value, then it is called a negative deviation. It is called the negative deviation. So first, it shows negative deviation. It reaches a minimum and then the value increases, shows a positive deviation. So in general, we can see that the real gases deviate much from ideal behavior. If the gas behaves as an ideal gas, it should obey Boyle's law. And if it obeys Boyle's law, the PV against the P graph should be a straight line parallel to the pressure axis. But practically, really, it is seen that in majority of the cases, the PV against the P, the graphs are not straight line graphs. These are not straight lines parallel to the pressure axis. That is expected for ideal gases. There is deviation. So the real gases deviate from the ideal behavior. There are two types of deviations. Positive deviation means there is a continuous increase in the PV value. And negative deviation, that is a decrease in the PV value. It reaches a minimum and then there is positive deviation. It increases. Anyhow, there is deviation from the ideal behavior for real gases. So the graphs obtained for real gases are not always straight lines parallel to the pressure axis or the volume axis. So we can come to the conclusion that the real gases deviate from the ideal behavior and they are not giving PV against P graph straight line parallel to the pressure axis as it is predicted for the ideal gases by Boyle's law. By Boyle's law. It is not obeying Boyle's law. And what is the reason for this deviation? This deviation is mainly due to two wrong assumptions in the kinetic theory of gases. The kinetic theory of gases. Kinetic theory of gases. You will study this in physics. It is not included in the present chemistry syllabus. It was there in the syllabus, but presently it is not there in our syllabus. Okay, I shall give you, say, an idea regarding the kinetic theory of gases. All these are the assumptions, predictions, assumptions given by the kinetic theory. Say, the important assumptions are this one. A gas consists of a large number of tiny particles called molecules. A gas consists of a large number of particles known as molecules. So a gas is composed of a large number of molecules. That is the first assumption according to kinetic theory of gases. This you need not study for our purpose. So I am giving you the postulates of the predictions, the postulates of kinetic theory of gases. So the first point is this: a gas contains a large number of very small, tiny particles called molecules. And the second assumption, the molecules are in continuous random motion. They are in continuous random motion, irregular motion, zigzag motion. So the particles or the molecules are in continuous random motion. There is no order. There is no order for the motion of the molecules. So they move randomly as they like, random motion. Then the third postulate is this: the pressure exerted by a gas, the pressure exerted by a gas is due to the bombardment of the molecules with the walls of the container. It is due to the bombardment collision, the bombardment of molecules, with the walls of the container. See, during the random motion of the molecules will be colliding with themselves and also with the walls of the container. There is no control for the motion of the molecules. So, due to the uncontrolled motion, the random motion of the molecules will be colliding with themselves and also with the walls of the container. The pressure due to a gas, the pressure exerted by a gas is due to the bombardment of the molecules with the walls of the container, So it is due to the bombardment, collision, bombardment and collision of the molecules with the walls of the container, pressure. Then the fourth assumption, see, there is no intermolecular force of attraction between the molecules. The molecules are free to move and there is no intermolecular force of attraction. There is no intermolecular force of attraction between the molecules. Between the molecules, there is no intermolecular force of attraction. But you remember the van der Waals forces. Remember the van der Waals forces. Van der Waals predicted that there is attractive force between the molecules, other than the ionic bond and the covalent bond. There are intermolecular force of attraction between the molecules other than the ionic bond and the covalent bonds. And these type of forces, attractive forces, known as van der Waals forces, that may be the London forces. Remember, you have seen the London forces, or it may be the dipole-dipole interaction, or it may be the dipole-induced dipole, or it may be the hydrogen bond even. Okay, so there are various types of intermolecular force of attraction between the molecules. But see here, in the kinetic theory, according to kinetic theory, there is no intermolecular force of attraction between the molecules. Then, the fifth assumption, the molecules are point objects, and therefore the molecules have no size at all. They have negligible size. Molecules have a negligible size compared to the total volume of the container. Usually, the volume of a gas is taken as the volume of a container. The gas spreads throughout the entire volume of the container. Therefore, the volume of the gas is taken as the volume of the container. Volume of the gas is the same as the volume of the container. That is our assumption. But so that is because the gas molecules are of a negligible size. That is a negligible size. And the sixth one, the average kinetic energy is directly proportional to absolute temperature, and that is equal to half mv square, and that is equal to 3 by 2 RT. 3 by 2 RT. So the kinetic energy is directly proportional to the absolute temperature. And that is a very good assumption. That is a very good assumption. There is nothing wrong in that. So let me see the assumptions again. Gas consists of a large number of molecules, very tiny particles, molecules. Molecules are in continuous random motion. Then the molecules will be colliding with themselves and also with the walls of the container. The pressure of a gas is due to the bombardment, the collision of the molecules with the walls of the container. Then there is no intermolecular force of attraction between the molecules. Then fifth one, the size of the gas molecules is negligible. The molecules have no size at all compared to the total volume of the container. And finally, we have kinetic energy directly proportional to absolute temperature, and it is equal to half mE square or 3 by 2 RT. And these are some of the assumptions of kinetic theory of gases. But among these, the postulates of kinetic theory of gases, these two assumptions are wrong assumptions. See, there is no intermolecular force of attraction. The theory, kinetic theory says, there is no intermolecular force of attraction. And that's a wrong assumption. Actually, there is attractive force between the molecules. And we call those forces as the van der Waals force of attraction. Then the size of the molecules, gas molecules, that is negligible. The gas molecules are of a negligible size. And these two assumptions are wrong. These are wrong assumptions. So due to these two wrong assumptions of the kinetic theory of gases, the real gases deviate from the ideal behavior. See here, point number 4, there is no intermolecular force of attraction. But in the real gases, there is intermolecular force of attraction. Okay, for ideal gases, we can say there is no intermolecular force of attraction. So that is true for ideal gases. But for real gases, there is intermolecular force of attraction. Second, the gas molecules are of a negligible size. The volume due to the gas, that is a negligible, that is 0. So that the volume of the gas can be taken as the volume of the container. But practically it is seen that these two assumptions, that is no intermolecular force of attraction and negligible size, these two assumptions are wrong. They are wrong in the case of real gases, especially at a low temperature and high pressure. At a low temperature and high pressure, there is strong intermolecular force of attraction. And at a high pressure, the size of the molecules cannot be neglected. We cannot take the volume of the gas as the volume of the container. In the equation PV is equal to nRT, the volume taken is the volume of the container with an assumption that the volume of the gas is equal to volume of the container. But that is not true in the case of gases at a low temperature and high pressure. So due to these two wrong assumptions, the real gases deviate from ideal behavior. And all these are the arguments due to van der Waals. All these are the contributions from van der Waals. Let us say the argument of van der Waals. So what did van der Waals do? He made a correction in the pressure and the volume also. He corrected the pressure as P plus AN square by V square. AN square by V square. He corrected the pressure like this. And the volume was corrected as V minus NB. That is equal to nRT. And this equation is called van der Waals equation or the real gas equation. Van der Waals equation or a real gas equation. Here, AN square by V square, that is called the pressure correction. Pressure correction. And here, A is a measure of the intermolecular force of attraction. A is a measure, that is a measure of intermolecular force of attraction. Intermolecular attraction. A is a measure of intermolecular force of attraction. It is also known as van der Waals constant. A is also known as van der Waals constant, and it is a measure of the intermolecular force of attraction between the molecules. So AN square by V square, that's called the pressure correction done by van der Waals. He increased the pressure. Here P is the measured pressure, or it is the real pressure. P is the real pressure. Real pressure means the measured pressure of the gas. So the ideal pressure, say P ideal, the ideal pressure is not the measured pressure. The measured pressure is P real. Real, that is the measured pressure. Real pressure, measured, that is equal plus an square by v square, an square by v square, where an square by v square is the pressure correction. So the ideal pressure, we have the ideal equation, ideal gas equation, PV is equal to nRT, and that P is the ideal pressure, V is the ideal volume of the gas. But here Van der Waals is of the opinion that the ideal pressure, ideal gas pressure, that is P ideal, must be greater than the real pressure measured. Real pressure measured. So the ideal pressure is equal to P real, that is pressure measured, P real plus a value due to the attractive force, that is an square by v square, and an square by b square is the pressure correction. Why the ideal pressure is greater than the measured pressure or the real pressure? Let us think of the bombardment of a molecule, bombardment of a gas molecule. See, a gas molecule, it is going to collide, it is going to bombard with the walls of the container. See, walls of the container. The gas molecule is moving towards the walls of the container. Then when it approaches the walls of the container, what happens? There are molecules behind and left and right. Suppose a molecule is here, behind this one, there is intermolecular force of attraction according to Van der Waals. So what will happen to the molecule that is going to collide the walls of the container? The molecule that is going to hit the wall, that is pulled back, that is pulled back by the molecule present in the backside of the molecule. So the measured pressure will be a lower value, which is expected for ideal gas. So the ideal pressure should be greater than the real pressure measured. The ideal pressure should be greater than the real pressure measured. Why? When the molecule is going to bombard the walls of the container, that molecule will be pulled back by the other gas molecules. Do you get the idea? This is the argument of Van der Waals. Argument of Van der Waals. So the gas molecule cannot hit, it cannot bombard the walls of the container with a pressure as expected for ideal gases. So the ideal pressure must be greater than that is measured. It must be greater than the real pressure measured. So there should be a correction for pressure. There should be an increment in the pressure. And that increment in pressure is an square by v square. So the ideal pressure, P ideal is equal to P real measured, P real plus an square by v square. And A is a measure of the intermolecular force of attraction. Now you think of you just think of the volume of the gas. Let us think of the volume of the gas. Say when pressure increases and pressure increases, what will happen to the volume of the gas? Let us take a cylinder like this, and here there is a piston, and here piston, and here there is a gas inside this. According to the according to Boyle's law concept, the volume of the gas is the volume of the container. Volume of the container. That must be the volume of the gas. But when pressure increases, suppose this is a 1 atm, 1 atmosphere pressure, then let the volume 1 atm, then the pressure is 1 atm, let the volume is equal to V. Say V liter, for example, V liter pressure. When pressure increases, what will happen to the volume according to Boyle's law? When pressure increases, what will happen to the volume according to Boyle's law? Rajas, Achyut, what will happen to the volume?
Decreases.
Decreases. I am asking the others, and the Punya is giving the answer. Well, keep it up. Okay, at least one student is here to give the answer. Pressure decreases. Now, volume decreases. Now, let's the pressure is increased by 2 atmospheres. Then the volume decreases. Let the new volume is equal to V2. V by 2, V by 2. Now, the what time? Same. Now pressure is increased by, say, 4 atmosphere. Then what will happen to the volume? Still it decreases. Say, let it
V by
be
4.
V by 4. Volume decreases and decreases. So finally, see, here we have the a very high pressure, let's say like this. This is the new pressure. Pressure is increased too much. Then the volume is decreased. Volume of the container is decreased. Now you consider the gas molecules. Suppose the gas molecules are spherical in shape. Spherical in shape. Then at a very low volume, that is high pressure. High pressure. At a very high pressure, the volume is very low. There is a low volume. So at a very low volume, the volume of the gas molecules cannot be neglected. If a pressure is too high, the volume will be very low. The volume will be very low. And under such a situation, the volume due to the gas molecules cannot be neglected. So the ideal volume in the ideal gas equation, the ideal volume should be lower than the volume due to the container. It should be the ideal volume, say B, ideal volume. It should be lower than, we are taking the volume of the container as the volume of the gas. But that is for an ideal gas. Same what happens. Okay. So the ideal should be less. It should be less than the measured volume. And so the real means volume of the container minus some value. And that value taken is, that is NB. That is equal to NB. That is to derive a new equation. NB, the volume should be, ideal volume should be this value, V real minus NB. And NB is called the volume correction. It is called the volume correction. Now we can apply this. We can apply this in the previous PV is equal to nRT equation, so that you will be getting this equation. P plus AN square by V square into V minus NB is equal to nRT, and that is the real gas equation, or the van der Waals equation for real gases. Here A and B are also known as van der Waals constants. They are also known as van der Waals constants. We can see that all gases will obey the ideal behavior at a certain temperature. And that temperature is called Boyle temperature. That is called a Boyle temperature, B-O-Y-L-E. B-O-Y-L-E. It is called a Boyle temperature or Boyle point. Usually it is seen that when pressure is low and the temperature is high, the real gases tend to be more ideal. The real gases tend to be more ideal when pressure is low and the temperature is high. High temperature, low pressure, more is the tendency to approach the ideal behavior for real gases. So that's enough for today. It is time. It is more than the time, I think. Anyhow, let me stop now.